with the chemistry of hypervalent iodine reagents. So, but before I start, I would like just to show you what was our motivation and how did we start our research. So we are a synthetic chemist research group, and our focus is around the functionalization and synthesis of nitrogen-containing compounds, and this is due to the remarkable importance of nitrogen in organic compounds, in small molecule approved drugs from FDA. At least 90% of these small molecule drugs have at least one nitrogen atom. So we have been developing hypervalent iodine reagents as tools to enable the formation of carbon-nitrogen bonds, but also sulfur-nitrogen and carbon-sulfur. And today the talk is about what we have been developing around these reagents and how we have been using them to form the carbon-nitrogen bond. But in our research group, we are also very interested in palladium catalyzed reactions to produce nitrogen heterocycles, in particular aza-indoles, indoles, and benzimetazoles. And we also have research on aminoglycans, and we have developed some synthetic routes to attain very versatile intermediates that resemble the bacterial cell wall peptidoglycan. And because we generate a lot of compounds in the lab, we have a couple of collaborations in medicinal chemistry with medicinal chemistry groups in which we put our molecules in use to answer key biological problems. But as I mentioned today, the talk is about hypervalent iodine chemistry, and I will show you two case studies from our recent research. And in the first one, I will show you how we have developed new reagents and how we have been using them in the transfer of primary amines to stabilize anilines. So our research started when we were interested in natural amino acids. And why natural amino acids? Because they can be, if you have access to them, you can modulate their properties and their biological activity and also physical chemical properties. And so for that, you know, this functionalization, so amination of the alpha-amino of the alpha-carbonyl position is really very attractive. And this has triggered kind of a gold rush towards procedures that enable the installation of an amino group alpha to the carbonyl position. So if you look into the traditional disconnections, you will find out that the most used approach is usually halogenation of the alpha carbonyl position and then simply displacement using a nucleophilic amine. And of course, it is good to have these disconnections in this procedure. Of course, you can also use metal catalyzed methods and they work. But the problem is that if you have more complex molecules, then it can limit the chemistry you can do. And this is the reason why the society has started to look at, the scientific community has decided to look at electrophilic amination procedures in which you can use these nitroso compounds or these diazo-carboxylate derivatives. But the problem is that you do not end up directly with the compound you desire. You end up with alpha-aminoxy or alpha-hydrazinyl, and this requires further steps to achieve the molecules that you want. So this is the reason why when we started this research, we thought, why not generating a primary electrophilic amine. And in order to access that, we decided to explore the chemistry of hypervalent iodine reagents. So why hypervalent iodine reagents? So you can describe them like this. So you know the iodine is a big atom. And with the iodine you can break the octet rule. And if you do the distribution, you will find that you have this electron pair. Your HOMO orbital is actually this one. So this is only half a bond. So this is weaker than a normal covalent bond. And the unique property of these compounds is because you have this weak bond, but you also have a very polarized bond. This means that any X or epsilon ligand that you put in here, it will be an electrophilic system. So this can mean that you can do prolonged reactivity, so you can reverse the polarity of your reagents. And recently, these cyclic ones, these benziodoxolones have emerged, and they are very attractive because they are even more stable than the acyclic ones, but they still keep the very high reactivity. So when we started our research, of course, we could already find in the literature several benziodoxolones, so these cyclic hypervalent iodine reagents bearing different nitrogen moieties, like for example, these azido benziodoxolones developed by Duncan, also from Jérôme Wasser, and other ones like sulfoxamines from Kastenbaum group. And when we were developing and we were writing our paper back in 2021, Shaoxian reported the first benziodoxolone bearing a secondary amine. So we reported our first benziodoxolones bearing a primary amine in 2022 that we have further expanded in 2025, as I will show you. And then in 2024, Minakata group in Japan reported this very useful benziodoxolone bearing this amino group, transferable amino group. So how we have started to prepare these compounds. So we were interested in employing them in electrophilic amination, and I would like to show you here the number of articles. This is electrophilic amination reports, but if you look back into the blue bars, which are the ones with hypervalent iodine reagents, you will see that they are almost underexplored. So when we started our research, Diogo and Ana Claudia, Diogo was a PhD student in the lab at that time, and together with Ana Claudia, they started with hydroxybenziodoxolone. And what they did is that they used the silylated benzylamine, and when you do it at minus 78 degrees and you let it overnight at room temperature in the acetonitrile, when we arrived in the next day, we had a very nice white powder at the bottom of the schlenk. And this was a very soluble compound that we could crystallize, and we realized that actually we had our benziodoxolone that we named BBX. This then we have further extended to other benzylated amines, even a chiral one. You can do this in a multi-gram scale. You can store them in the bench or even store it longer if you keep it in the fridge. They are crystalline. We could do X-ray analysis of all of them. And as you can see this very T-distorted geometry, which is characteristic of this kind of compounds with the ligands almost linear arrangement. And curiously, in our reagents, this nitrogen iodine bond is even shorter than the format reported benziodoxolones bearing nitrogen motifs. So we could prepare them, they are stable, but were they useful? This is exactly what we explored next. We used this indinone beta-keto ester as a model compound. We screened many conditions. I have shown you here some, and we found out that when you perform the reaction at 80 degrees with using potassium carbonate, you get a very good conversion of the transfer of the benzylamine into the alpha position. And then we could even remove the benzyl group and attain the unnatural amino acid. So we have also explored the reaction in the presence of tempo. As you see here, this is entry 16 from the table. And when we did this, the yield dropped considerably. So we thought maybe the reaction was undergoing in a radical mechanism, and I will show you next. So next, we explore the scope of the reaction, and we could transfer the amines, the primary amines of all the BBX to different indinone beta-keto esters, in which we have explored not only the ester group, so even with very bulky ones, we got good conversion, but also other benziodoxolones, for example, having a methoxy in the aromatic or a methyl group, or even with the chiral one, in this case with very low diastereoselectivity selectivity. So regarding the mechanism, as I've told you, we have explored the combination of mass spectrometry studies with DFT calculations. We have used, so we have analyzed all the separate elements, so the tempo with only the BPX and the tempo only with indinone. And we found out that actually when we could detect the formation of these adducts that results from the reaction of the indinone with the tempo. And this is the reason why our yield decreased so much when you perform the reaction in the presence of the radical trap. It's not because there is a radical reaction undergoing with our BBX, it's just simply because you form the adduct from the indinone salt, because you do need to preform the anulate if you want the reaction to work. And this is also already a clear indication that there is no radical mechanism involved. And the DFT calculations have also further supported this, and we found this transition state that results from nucleophilic attack of the nucleophile directly in the nitrogen, followed by reductive elimination. So next, in my second case study, I will show you how we have expanded this library of compounds and how we have put them to use, but now combining the reactivity with the functionality of organozinc reagents. So as I told you, we were the first ones to report these benziodoxolones that allow you to prepare secondary amines. The ones from the shell chain, if you want to transfer this piperidine or morpholine amine, you will end up with a tertiary amine synthesis. And if you use Minakata reagent, you will end up with a primary amine. So we decided to explore the activity now with different carbon nucleophiles. And for this, we did a collaboration with Professor Boeknogel, and we explored these polyfunctionalized and very stable organozinc reagents. So you can prepare them, you can access a library of these organozincs, and then we could combine them with different BBX reagents. So just to show you, this was our first expanded library of benziodoxolones, and you can see that we have many different amines, some chiral ones. Also, this indenone, we got out only trace amount of these, but with the dimethyl or even with amino acids, bearing, for example, this N-bok-proline, we were able to produce the responding benziodoxolones in very good yield. So next, we have to establish the conditions. And now I have to say that we were happy to find that the reaction goes even without the metal catalyst. But if you use copper acetate, you have an increased yield, and also the reaction is faster. So we have also established a protocol for the formation of the organozincs, and we could observe that the zinc p-valate was indeed the best reagent. And then Anna, Jose, and Beatriz, that were PhD students in the lab, they have explored the versatility of this protocol. So once the protocol is established for our model reaction, we explore different benziodoxolones. And here we kept the first one with the phenol zinc p-valate. And you can see that we have the corresponding amines in good yields, but also with pyridyl ones, it works pretty well. And even with chiral ones, and you can keep the chirality. And of course, with the carboxy ethylphenyl, the cyano, or even with the trifluoromethylphenyl, the reaction, you can attain, you can achieve the corresponding secondary amines. So we have expanded, we have applied the protocol to the synthesis of APIs, and we selected this benzonatate, which is actually used on the relief of symptoms from several respiratory conditions. And in order to do this, we prepared this benziodoxolone bearing this butylamine. We reacted with the corresponding zinc p-valate, and we achieved the secondary amine, and then just simply standard transformations up to the benzonatate. We have also explored investigated the mechanism of this reaction in collaboration with Professor Jaime Coelho from the Faculty of Science in the University of Lisbon. And what we realized is that actually what we propose is that so we need two equivalents of the organozinc. The first one to make the deprotonation of the BBX, and then there is the formation of this tetra-coordinated anionic organozincate, that then, so due to an increase in the electron density on the zinc, it promotes a 1,2 aryl migration. And in the presence of copper, we propose that the role of the copper is just to facilitate this migration by acting like a Lewis acid. So you can see that the transition state is lower in energy. So to finish, I hope that I could show you that these benziodoxolone reagents are really useful, that you can use them to different transformation with the different carbon nucleophiles. And if you would like to know more about our research on hypervalent iodine chemistry, I will show that we have also expanded the use of chlorobenziodoxolone and other derivatives and use them to produce, for example, sulfonamides, sulfonyl hydrazines, more recently this year on sulfones. And if you want to know more about our research, we can just access or just contact us through our social media or even our website. So to finish, I would like to, of course, to thank to my team, to my very dedicated research team, of course, also to my collaborators, especially to Professor Portugal with the work that I have shown you here, and also to Jean, to Stefan Brez in KIT, in which our compounds are being now also, we have a very good collaboration with Professor Stefan Brez regarding the production of now primary amines that we are currently developing, and of course to the funding agencies and to all of you for your kind attention. And of course, I'm happy to answer any questions you might have.
Thank you, Doctor. Thank you for your presentation. Now the session is open for queries. Any questions, please?